think we will start in after a couple of minutes. Maybe someone else might join. I think we can start. So let's start. Good afternoon, everyone. My name is Musab Rafiq. I'm a course TA for this course on digital circuits that's taught by Professor Shantanu Chattopadhyay of IIT Kharagpur. This is live session 5. In this live session, we'll be discussing problems related to your week 5 material. So that will be helping your assignments and all. So if there are any doubts and queries, I'll be giving few minutes after every question. And to all those participants who will be joining late, I'll be admitting them once I'm done with a particular problem. So let me just admit some people here, and then we can start with the first problem. So let's start. So this is our first problem. So in this tutorial, we'll be dealing with mostly with problems from mux, decoders, and BCD addition, accessory codes, and all. So this is our first problem. It states that in the following circuit, X is given by. So here what we have a 4 is to 1 mux, and the output of this mux is connected to another 4 is to 1 mux, and we are required to find this X. So what will be this X? So let's start. So what we have here is these A and B. These are inputs, and these are variables A and B that are input to the select lines S0 and S1, and these are our input lines to the mux. So here what we have is A and B, and once A B is 0 0, then this line gets selected. Once it's 0 1, this line gets selected. When it's 1 0, this line gets selected, and when it's 1 1, this line gets selected. So we can write our equation of, I will just this is y. So y will simply be equal to a bar b bar, but that time input is 0, so that will be 0 only, plus a a a bar b. A bar, when I'm referring to a complement, so keep that in mind. A bar b, and it's 1, so 1 gets ended, plus a bar b, and finally we have 0 again, so y will simply be equal to a bar b plus ab bar. So this, sorry, let me just correct, this is bar here. A bar b plus ab bar. Now this y, it goes to the select line of this mux. So this is again, it's the same. So X will simply be equal to, here A is Y, so X will be equal to Y bar, and B is C, Y bar C plus YC bar. If you can look at this configuration is same, but the only difference here is that this A is replaced by here Y, which was the output of this mux. So X is equal to Y bar C plus YC bar, and this Y is this A bar B plus AB bar. Just substituting this Y into this, so we have A bar B plus AB bar, and we have complement to this, whole complement, and it's with C plus Y. Y is A bar B plus AB bar dot C bar. Now, what we have here is, if you remember, this is a bar b plus a b bar, and its complement. This is, we know that this XOR, if you can recall it, XOR. I'm just showing you one shortcut to this. XOR is simply a bar b plus a b bar, and once you complement this thing, it becomes XNOR. So which is a b plus a bar b bar. So I'm just saving some few steps here, so I can directly write this thing. So a bar b plus a b bar is simply a b plus a bar b. So what is this step? A bar b plus a b bar whole bar is simply a b plus a bar b bar, and c. Let's just multiply them. So this is a bar b c bar plus a bar b bar c bar. Now multiplying the first term as well. So this is a b c plus a bar b bar c plus these terms a bar b bar, sorry, it's not bar, a bar b c bar plus a b bar c bar. So if you look at this, this is option a b bar c bar this term, a bar b c bar this term, a bar b bar c this term, and a b c this term. So option A is answer to this problem. If you have any doubts and queries, please let me know. I'll also admit some students who are waiting. In case of any queries, any doubts regarding this question, please type in. So I guess there are not any doubts regarding this problem. We can move forward to this next problem, which is question number 2. So the question number 2 asks us the Boolean function f. The Boolean function f implemented as shown in the figure using two input multiplexers. So here we have 2 is to 1 multiplexer, and the output of this is connected to the select line of another 2 is to 1 multiplexer, and we are required to find out this output f. So what we have here is, so for a 2 input 2 is to 1 multiplexer, 2 is to 1, we have two input lines I0 and I1, and we have this select line S. So the output is simply equal to y is equal to S bar I0 plus Si1. So what we have here is, so if I can term this output of this mux here as x, first one. So my output of first mux x will simply equal to b bar c plus bc bar. Now this x is select line of another 2 is to 1 mux. So my f is equal to, so they have termed it as e, we can call it as x also. So f is simply equal to x, so o, this is 0, this is x bar plus x a, so it is 0 a, so this is simply x a. Substituting the value of x here, we have our expression as f is equal to, so x is b bar c plus b c bar multiplied by a. So f is equal to a b bar c plus a b c bar. So if you can look at the options, this is I think A B bar C, A B bar C plus A B C bar. This is option A. So the correct answer to this question is option A. If you have any doubt, please type in the chat box. So I can see there are no further doubts, or there wasn't any doubts regarding this question. We can move forward to the next question. That is question number 3. So the question number 3 asks us to find the output of the circuit shown in figure. So the figure is given here. So what we have here is again 2:1 mux connect whose output is connected to another input line of another 2:1 mux. Then whose input output is again connected to the input of another input line of another 2:1 mux, and we are required to find out the output. These are the select lines whose values are given. Now let me first redraw what a 2:1 mux essentially does. Some people have joined in, that's why I'm repeating this stuff. So we have this 2:1 1 mux, and here we have two input lines I0 and I1, and here we have this select line, and here it is our output. So Y is simply equal to S bar I0 plus Si1. So what it essentially means, when S is 0, this input line will be given to the as output, and when S equal to 1, this input line, the data on this input line will be given as output. So what we have here is we have this two input mux connected together. First one, let's see what will be the output of this first one. Let me just label them 1, 2, and 3. So this is first one. So here we have 0 and here we have 1. So input 0, at input line 0 we have 0, and input line 1 we have 1, and select line is 1. Select line condition is given as 1, so this input will be selected, that is I1. That means our output will be 1. So X, so this our output is equal to 1. Now this is connected to another 2:1 mux, so which I have labeled as 2:1 mux, and this is connected to I1 data line, and at I0 data line we have input which is connected to this variable X, or we can say this is our input X. So now the select line has a condition equal to 0. So when S is equal to 0, this will be given as output. So our output will be simply X. Output will be I0, and I0 we have this value X. Now X is given to another 2:1 mux. So this 2:1 mux is I have labeled it as number 3, and here is our output which we need to find. So this X is connected at I1, and also at I0 we have this input as per question. This is A. So here finally we have this condition on this third mux as select line is 1. So anything coming from this will be present at the output. So what was our output? So input was X, so this will go to the output. So our output will simply be equal to X. So if this is an option, yes, option B is our correct answer. So if there are any doubts regarding this question, please type in. If you want me to repeat, I can repeat. Some people have joined in. If they want me to repeat this question number 3, I can repeat, or else we can move forward to this question number 4. So I saw some people joining in late. Do you want me to repeat question number 3, or we can do it later? Okay, I can see people are saying go ahead. So I'll just proceed with question number 5. Question number 4. We can just come back to it later. So question number 4. Now moving forward to this question number 4. So the question number 4 is a theoretical question. It says that in a multiplexer there are 4 input lines and 1 output line. So we are given a let me just so in a multiplexer, if there are 4 input lines, so we have 4 input lines. 4 input lines and 1 output line. So it is a 4 is to 1 mux. Then the number of selection line is so the question simply asks us to find out the number of selection lines for 2 is to 1 mux. For 4 is to 1 mux. So we simply know that uh, for any multiplexer, if it's for any multiplexer with n select lines, we can write it as 2 raised power n is to 1. So here n represents our number of select lines. So comparing these two, we have 2 raised power n is simply equal to 4. That is simply n is equal to 2. So for a 4 is to 1 mux, number of select lines we have is 2. That is S0, S1, and our 4 input lines are represented by I0, I1, I2, and I3. So for a 4 is to 1 mux, the number of input lines is select lines sorry is 2. Option C. And I think this was a pretty simple question. I think we can move forward to the next question. So moving on to part 5, question number 5. Sorry. So the question number 5 is question based on the decoders. So we have a 3 is to 8 decoder. A 3 is to 8 decoder is shown in the figure. So we need to find the f. So f of x2, x1, x0. So these are the input variables x2, x1, x0. So we are required to find the function corresponding to this condition. So let me just redraw it here. So this is a tricky question in fact. D0, D1, D2, and D3, D4, D5, D6, and D7. And our inputs are x0, x1, and x2. So 1 is connected, 4 is connected, and 7 is connected. The reason I said it tricky is because of this gate. Usually one has a OR gate connected to here, but here the question has given us NOR gate. So this is the tricky part here. Rest is pretty much simple. So what happens here? So if it simply was an OR gate, F would simply have been equal to, so this thing D1 plus F would simply have been equal to D1 plus what is this thing D4, D1 plus D4 plus D7. So F would have simply been equal to sum of minterms 1, 4, 7. But since the gate here connected is NOR gate, so this NOR gate gives us the value 1 when all of the inputs are 0. So if you can say, refer to the truth table of a NOR gate, here I am trying truth table for a 2 input NOR gate. So when both inputs are 0, it will be 1, and when one of the input is 1, it will be 0. So this thing will be 1 when all of when these three are 0. So these three will be 0 when we have these three 0. So this will be equal to the complement of this thing. So f will simply be equal to summation of all those terms that are remaining. And apart from 1, 4 and 7, all those terms that are remaining. So f will simply be equal to sum of min terms 0, 1 will not be there, 2, 4, 3, 4 will not be there, then it will be 5, and then it will be 6. So f will be simply equal to sum of min terms, because when they are 1, if when any of them is 1, this will be 0. F will be equal to 1 when all three of them are 0. So they will be 0 when any of them rest of them are equal to 1. So we have this thing, f is equal to sum min terms 0, 2, 3, 5, 6. The trick part here was this NOR gate. If it would have been an OR gate, it would simply have been f is equal to sum of min terms 1, 4 and 7. I hope I was clear with this part. In case of any doubts, please type in. Yeah, I'll repeat. Wait, I'll repeat. So we can draw a new slide here. So decoder is connected to 1, 4 and 7. So here we have x0, x0, x1, x2, and the input line was connected to this is D0, D1, D2, 3, 4, 5, 6, 7. Please read them as D3, D4. In the interest of time, I am not writing them. And 1, 4, and 7 are connected to NOR gate. So if we can look at this D1 is simply equal to x0, x2, x1, x2, and this is x1. So this G0 is this thing. D4 will be this is not bar. Don't consider it bar. And D7 will be x2, x1, x0. So if it was an OR gate, let's consider for a moment it was an OR gate, our F would have been like this. But since it's an OR gate, you have to complement these things. And when you complement this thing, it will simply come out to be the sum of remaining minterms, which are not connected to this gate. So once this thing is 1, 1, and once this thing is any of the D1, when any of this combination is 1, f will be equal to 0. But f will be equal to 1 only when this rest of the term, f will be equal to sum of minterms which are not connected to the NOR gate. So f will simply be equal to summation of m 0 to 0, 2, 3, 5 and 6. So let's just check. So when x0 is when let's check for a 0, 0, 0 case. Let's just draw a truth table to elaborate it for some cases. Let's just try 4 cases: 0, 0, 1, 0 and 0, 1, 1. So this is our minterm 0, this is our minterm 1, this is our minterm 2, and this is our minterm 3. So when this x0 is 0, 0, 0, so this input line should be selected, but it's not connected to any of the gate forward. And when input is 0, 0, 1, so this is 0, 0, 1, this will be selected, so this will be high. So once this is high, our f will be equal to 0. So this f will be equal to 0 once for the min-term combinations 1, 3 and 7. But f will be equal to 1 for the min-term combinations, rest of the min-term combinations 0, 2, 3, 5 and 6. So let's say our input combination was 0, 0, 0. So this thing would have been selected, but it's not connected to f, so all of these would have been 0, but our f will be 1. So our f will be 1, so we can draw our truth table like this: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. So if you our f will be equal to 1 at 0, at 2, at 3, at 5, at 6, and for the rest of the three cases it will be 0. So if you simply write this is simply f of summation of minterms 0, 2, 3, 5, 6. I hope I'm clear. So let's just consider at the end of the day we have to find f whenever f. So just draw the truth table, simply draw the truth table for all of these cases and just see write them in terms. You just take a look at truth table. I hope you can see the truth table. Are you seeing the presentation? Shankar, if you can reply to in the chat, are you able to see the presentation right now? Any screen? Okay. So just look at the truth table. It's kind of shabby, but still you will get the point. Just take a look at all the cases whenever the input is 1. So input is 1 at the minterm 0, 2, 3, 5, 6. So if you have to write it in the summation of product forms, sum of product forms, so how will you write it? So you will simply write f is equal to summation of m of 0, 2, 3, 5, 6. Yeah, it is just an elaborative way. They simply would have been take the complement. F was equal to 0 for those two three cases, and for rest of the cases it would have been 1. So that's why I was saying that it would be 1 for remaining cases. But to confirm the things, we can draw the truth table. If it would have been an OR gate, what would have been our output? F would have been equal to summation of minterms 1, 4 and 7, right? Now it's an OR, this NOR gate, so it will be high for remaining cases. But truth table makes our life easy, but sometimes you don't have time to get to truth table, so we just use the shortcuts. I hope I was clear. I think I made it a bit of a mess. It was a pretty simple question. I think this AND case would be then we'll be dealing with product of some thing. I think we'll be dealing then product of some cases. This OR and NOR case are dealing with sum of product cases. Then we'll use this pi rather than summation. That's a different case. You can try that. So moving forward to question number, this was question number 4, I guess. Moving forward to question number 5. Sorry, question number 6. So question number 6 is also based on this multiplexer. So question number 6 asks us to find the output of the function, find the function f. So here we have to is 2 to 1 mux. So we are required to find the f. So for a 2 to 1 mux, we know that y is equal to s0 s bar i0 plus si1. So here this a2 and a3 are let's just draw mux here. This is our 2 to 1 mux, and my select line to this mux is a1. and the input is input, let's say this, consider this input as I0 and this is I1. So if you carefully examine this figure, I1 is simply AND. I1 is simply AND of A2 and A3. I1 is sorry, I0. I0 is simply AND of A2 and A3. I0 is equal to A2, A3, and I1 is OR of them, A2 plus A3. So we are required to find F. So F will simply be equal to A1 bar I0 plus A1 I1. If you have time, always break these problems into steps. That will be quite helpful. So substituting the value of I0 here, so it is A1 bar I0 will be A2 A3. So this is A2 A3 plus A1. I1 will be what is I1? A2 plus A3. I2 A2 plus A3. So writing down again A1 bar A2 A3 plus A1 A2 plus A1 A3. Taking A2 common between first two terms, so A2 is common, so it will be A1 from this term, and this will be A1 bar A3. A1 plus A1 bar A3, and my other term will be A1 A3. So we know this property, A plus A bar B is simply A plus B. So here A is A1 and B is A3. So this is A2 A1 plus A3. This is A1 plus A1 bar B. B here is A3 and A is A1. So this will be A1 plus A3, and this is final term is A1 A3. A1 A3. So my final answer will be A1 A2 plus A2 A3 plus A3 A1. If you carefully look at this, this is option A1 A2 plus A2 A3 plus A3 A1. This is option A. Any doubts regarding this question? Question number 6. So we can move forward to this next question. Question number 7. So in a binary coded decimal system BCD, the number 81 is represented as. So we have to represent 81, which is in decimal, in BCD representation. So we will take these two digits separately and write a 4-bit binary representation of them. So 1 in 4-bit representation is 0, 0, 0, 1, and 8 in binary 4-bit binary representation is 1, 0, 0, 0. So writing down 1 here as 0, 0, 0, 1, this part, and 8 as 1, 0, 0, 0. So my BCD representation of 81 is 1, 0, 0, 0, 0, 0, 0, 1. So this is option 1. So this is option A. Option A is correct answer to this question. I think this was a pretty straightforward question. I'll just move forward to the next question. That is question number 8. So question number 8 asks us to find the addition of 96 plus 69 in BCD is. So the addition of decimal numbers 96 plus 69 in BCD format will be. I'll just show the two ways to do this. First is simply just write down the number in decimal format, that is 96 plus 69. So if you just add them, so 9 plus 6 is 15, 1 goes to carry, 9 plus 6 is 15, 1 is carry, so 165. Just write the BCD representation of them. For 5, 4-bit binary representation will be 0101. For 6, it will be 0110, and for 1, it will be 0001. So writing down the representation: 0101 for 5, 0110 for 6, and 0001 for 1. So the number will be 1011000101. So this is number option C, if you can check it. Now first another method is just converting 96 into BCD. 96 in BCD will be 1001 and 0110, and 69 will be 0110 1001, and just add them up. So 1 is is 1, 1 plus 0 is 1, 1 plus 0 is 1, and 1 plus 0 is 1. 1 plus 0 is 1, 1 plus 0 is 1, so this is 1. If you carefully look at them, this is an illegal representation in BCD. So according to the convention, so what we add is we add 6 to both the numbers. So 0110 and 0110, we'll add them. This is, so 1 plus 0 is 1, 1 plus 1 is 2, that is 1 goes to carry, 1 goes to carry, 1 plus 1 plus 1 is 3, 1 goes to carry, 1 plus 1 is 0, and 1 goes to carry, 1 plus 1 is 0, and 1 goes to carry, 1 plus 1 plus 1 is 1, 1 goes to carry, 1 plus 1 plus 1 is 1, 1, so 1 goes to carry, and plus 1 is 0, and 1 goes to carry, so it will come down here. So our number will be 1011000101. So that is option C. So I showed you the both way how to do it. This one is pretty much easy. In this thing, if you get an illegal representation that is greater than 9 comes out to be here, we need to add 60110 to each of the this number. So I'll just add some students up, then we can move forward to this question number 9. That's why we add 6. So now moving forward to this question number 9. Question number 9 states the logic function implemented by the multiplexer circuit is logic function implemented by this is, and where ground implies by logic 0. Usually logic 0 is represented by the ground if stated otherwise. So we are asked to find the output of this thing. So for this is a 4 is to 1 mux. So F will be equal to, let's just first write down the inputs of all the cases. So this ground represents 0. Let's just write I0 first. I0 will be equal to, so this 0 thing goes to this NOT gate, so it becomes 1 here after NOT gate, and this NOT gate again goes, this 1 again goes to another NOT gate, so this would be 0. So I0 is 0. Then we have I1. So I1 is this 0 goes to NOT gate, it becomes 1, so I1 is 1. So this is 1, this is 0. I1 is 1. So this for I2 as well, this is 1, and now we have this I3. I3 is simply directly connected to ground, so it is 0. So we know for a 4 is to 1 mux, or we write our function f is equal to s. Let me just write it as s0, I0, s1, s s0, s1, s0, I1, s1, s0, I2 plus S1 S3 I3. So here are I0 and I3 are 0, so only these two terms will be considered. And here S2, here S1 and S0 are P and Q respectively, so it will be P bar Q plus PQ bar. Just writing these two terms. So S F will be equal to P bar Q plus PQ bar, so F is equal to P XOR Q. So our this function represents a XOR gate between P and Q. That is option D. This I3 and I0 were 0. That's why these two terms became 0, and this I1 and I2 were 1. So only these two these quantities are considered here: P bar Q plus PQ bar. So in case of any doubts, please type in. Otherwise, you can move forward to the next question. Question number 10. So question number 10 asks us how many 2 cross 4 decoders are required to implement 4 cross 16 decoder. So there are five five 2 cross 4 decoders are required to implement a 4 cross 16 decoder. So this is our first decoder. To which two inputs A and B are connected, and this is the enable to this. Here we get the output. So what in 4 cross 16 decoder, what we will have is we will essentially have 4 input lines and 16 output lines, and there will be an enable. And now we have this. We will connect output of this decoder to other 4 decoders, other 4 2 cross 4 decoders. These all are 2 cross 4 decoders. These all are 2 cross 4. Keep that thing in mind. These all are 2 cross 4 decoders. So the output from this out from this first decoder goes to as enable to all the decoders, other decoders. Sorry, this is I2. This is connected here. This is connected here. This thing is connected here, and the fourth one is connected here. And my other two inputs will go to all the 4 decoders: C, D, C, D, C, D, and C, D. So this will be this will be Y0 to Y3. This will be Y4 to Y7. This will be Y8 to Y11, and this will be Y12 to Y15. If you carefully examine, so once let us consider enable is high. So once A and B are 0 0, this input line is selected, this 0th D0, and this D0 turns on this decoder. So this D turns on this decoder, and to turn on these output lines, it will depend on the combinations of these three. So for this, we can just write it down like this: A B. So A B will be turned on. This encoder, I'll just name it decoder. Sorry, decoder 2 will be turned on only when A B is 0 0. So when A B is 0 0. And for other cases CD will have 4 cases: 0 0, 0 1, 1 0, and 1 1. So when this is 0 0, we'll have y0 selected, and when this is 0 1, we have y1. Once this is 1 0, we'll have y2, and once this is 1 1, we have y3. So finally, and once the input combination AB is 0 1, this decoder D2 D3 will be selected. Once this is 0, this 1 0, this will be turned on 0 D4, and once AB is 1 1, this decoder will be turned on. So ultimately, what we'll have, ultimately what we'll have we will have for four input combinations. A, enable is one. Consider enable is one. A, B, C, D. We will have 16 cases: 0, 0, 0, 0, 1, 0, 1, so on up to 1, 1, 1. And in this case, y16 will be 1, so this will be y16, and in case y1. So truth table will be somewhat like this. You can draw the truth table. It will be simply a truth table for a 4 cross 16 decoder. Any doubts regarding this question? So I can see there are no doubts regarding this question. We can move forward to the next question. That is question number 11. So this is a simple question. It simply asks us to find the accessory code of the following decimal number. So how will we find the accessory code of the decimal numbers? First, we will convert the decimal number into BCD representation. So 24 in BCD will be represented. So 4 is present in 4-bit format as 0, 1, 0, 0, and 2 will be represented as 0, 0, 1, 0. So in access 3, we'll just add 3 to both of the number, this representation 0, 0, 1, 1. So this will be 1, 1, 1, 0. This will be 1, 1 plus 1 is 0, 1, 0, 1, 0. So it will be 0, 1, 0, 1, 0, 1, 0, 1, 1, 1. So 24 accessory code will be 0, 1, 0, 1, 0, 1, 1, 1. So if you just check it, it is 5, 7 BCD. 5, this is 5, and this is 7. Now we have another number, this is 6, 5, 8. 6 will be represented as 0, 1, 1, 0. 5 will be represented as 0, 1, 0, 1. 8 will be represented as 1, 0, 0, 0. Adding 3 to both access 3, 1, 1, 0, 0, 1, 1, 0, 0. So this is 1, 1, 0, 1. This is 1 plus 1 is 0, this is 1, 1 plus 1 is 0, this is 1, 1 plus 1 is 0, and this is 1. This is 1, 1 plus 1 is 0, this is 1 plus 1 is 0, this is 1. So this will be accessory representation of 6, 5, 8. This is 9, 8. So accessory code of the following decimal numbers are these. Now move to the next question. So we are asked to implement the Boolean expression f of a, b, c equal to sum of minterms 2, 3, 6, 7 using a multiplexer. Since there are three variables, so the 2 raised power n, for n variable, the number of the multiplexer required to implement that thing is 2 raised power n cross 1. So number of variables is 3, so we needed 8 cross 1 multiplexer here. So what we'll do is we'll just draw a multiplexer, 8 cross 1 multiplexer, having I0, I1, I2, I3, I4, I5, I6, and I7. And all the inputs will be given as select lines. You know that for a 8 cross 1 multiplexer, we have 3 select lines. Those 3 select lines will be connected to the inputs A, B, and C. So this thing is equal to 1 for these minterms 2 3 5 2 3 6 7. So 2 is simply a b c. So 2 is connected, 2 will be connected to 1, 3 will be connected to 1, 6 will be connected to 1, and 7 will also be connected to 1. So this thing is connected to 1. And all the other input all other inputs will be connected to 0. So in this way we can just have this boolean expression using a multiplexer. Now moving forward to the another question. Here we again have three variable function f of a b c, and we are asked to implement summation of 0 2 5 6. But here the catch is we have to only use a 4:1 multiplexer. So we know that for a n plus, if we have a n plus 1 variable system, so we can implement the function for n plus variable with 2 raised power n cross 1 mux, where n variables are connected, all these significant variables are connected to slate lines, and the one remaining variable is given as input. So here we'll take the help of the implementation table to find the required cases. How do we connect input? How do we connect input to the input of the multiplexer? So B and C input, B and C will be connected to the select lines for a 4 cross 1 mux, and D will be connected as the input lines. So to how to connect D? So for that we'll draw an implementation table. So implementation table will be like this. This will be 0, D0, D1, D2, and D3. Here it will be A bar and it will be A. So this thing, this thing, this thing. Here we'll write 0. This represents the minterms 0, 3, 4, 5, 6, and 7. So we will encircle all those minterms which are 1. So this is 2, 0, 0, 2, 5, and 6. So since this thing corresponds to A bar, we'll just write it as A bar. This thing corresponds to A, we'll just write it A. Since both of the terms are encircled here, it will represent as 1. And for this, is none of the terms are encircled, it will represent as 0. So the above given function will be represented by 4:1 mux. By connecting this I0 to A bar, so we will have this A coming like this, going to a NOT gate, and A will be connected to D1. D2 will always, I2 will be always equal to 1, and D3 will be 0 connected to ground, and our two select lines will be B and C, and my output will be F. So this is how we'll implement a n plus 1 variable system with a 2 raised power n cross 1 multiplexer. Now moving forward to this question number 14, the last question of today's presentation. So this is again just like a previous question, where we have asked to implement a 4 variable function, but using a 8 cross 1 multiplexer. Otherwise, we would have been we would here use BCD will be our select lines and A will be to our input. So we'll just again construct a implementation table for this. It will have 7 columns, because input to 8 cross 1 has 8 columns. Sorry, 8 columns. 1, 2, 3, 4, 5, 6, 7. D0, D1, D2, D3, D D4 D0 1 2 0 1 2 3 4 5 6 7, and this will be like this. Here, since A is there, this will be A bar, this will be A. So I'll just write down the number of midterms: 2, 3, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Now we will encircle all those midterms: 0, 1, 5, 6, 8, 10, 12, and 15. Since both the midterms are encircled in this column, so it will be 1. Only this one is encircled, it will be A bar. Only this one is encircled, this will be A. Both of them are encircled or not circled, so this will be 0. Only one of them is encircled, and that too in the A. This will be A bar. This will be 6 is encircled, 6 is encircled, this will be A bar again, and finally A. So these will be our 8 input lines to the mux. This will be I0, I1, I2, I3, I4, I5, I6, I7, and my other two will be select lines. So I0 will be connected to 1, this will be connected to A bar, this will be connected to A, this will be connected to 0, this will be connected to A, this will be connected to A bar, then also A bar, and finally A. And this will be the two select lines, and this will be my output. So in this way, we can implement the function using a 8 cross 1 multiplexer. If this was not specified, we could have also implemented it using 16 cross 1 multiplexer, where all the 4 variables would have been given as a select lines, and other cases would have been given the input lines would have been connected to only 1 and 0 according to the given question. So this was all for today's tutorial. I hope you guys have understood the problems, and this will help you with your assignments. So we will again meet next time at, yeah, can you please type it? Your audio is not clear. Question number 13, you want me to repeat it? Question number 13, yes, this one. Yeah, you just want to take a screenshot of it or something else? Your audio is not clear, I'm not able to hear you properly. If you can, sorry, it's still not clear. In case of any doubts, you can refer to the recordings. So I'm not able to hear you properly. Sorry for that. Answer of question number 6. Okay, you want me to give the answer of question number 6. Question number 6. Answer of question number 6 is part A. Yeah, multiplexers usually have, sorry, decoders usually have this enable line. Yeah, because if you sometimes you want to disable a particular decoder, we don't want to use any of the conditions, and we always want the output to remain as low or high. So we just have enable for that. It just gives us an extra bit of liberty. So when enable is low for a low, where enable is connected, so when enable is low, our input conditions become a don't care conditions. So our output lines will always be at low. So if there are not any further questions, we can just end today's session. Thank you so much for joining. We'll again meet at this time next week, Sunday, 3 to 4 p.m. where we'll be discussing the problems related to week 6 tutorial. Thank you.